Thank you for the introduction, and thanks for the invitation to speak here. This talk is based on the paper called Soft-Dual Matroids from Canonical Curves, which is joint work with Sachi Hashimoto, Bernd Stumpfels, and Raluca Vlad. And today I'm not going to tell you about canonical curves, but I'm going to tell you instead about the tropical Grassmannian and soft-dual matroids. So for the start, I'm going to recap definitions of matroids. I know we've seen them already yesterday in Benjamin's talk, but to be on the same slide and have the same notation, I'm going to say matroid for us is an ordered pair of a subset B of the power set of a finite set E, and B has to satisfy two axioms. It's not empty, and it satisfies the basis exchange axiom, which also we've seen yesterday, right? So that whenever I have an element X in B1 but not in B2, there is an element in B2 but that's not in B1, so that I can exchange these two elements, and it's still a yes.
B is empty, then B should be allowed to be there.
Yes, okay. It's a finite non-empty set. Thank you. Yes. We want a non-empty finite ground set for the matroid. Yes. Yeah. That's true, but we're gonna only look at
Basis with the set with the empty. I mean, collection of bases.
Oh right, yeah, Benjamin, you're right.
Ah.
Benjamin is right. Oh, sorry. Great. Okay. Okay. So yes. Thanks, Benjamin. Okay. Yeah, so we have the set B of the bases, and the cardinality of every basis is the same, and this is called the rank of the matroid. Okay, and as an example, there is the so-called uniform matroid. I think we've also seen that yesterday, of rank R on M elements, where every basis, where all the bases are just subsets of size R of the set 1 to M. Okay. Now, what we've also seen yesterday is that the idea for matroids comes from vector spaces and bases, or from matrices. And this is, oh, I have another, yeah, a concrete example for the uniform matroid. I forgot. So for 1, 2, 3, we have all the two element subsets of 1, 2, 3, 4. And this is the uniform matroid 2, 4, which we'll see a couple of times in the talk as our baby example. Okay, so as I said, matroids, the theory is a generalization from the theory of vector spaces and bases. And we've seen this yesterday as well. There are matroids that are called realizable, which we can get by fixing your fields and writing down a matrix. And then the columns of the matrix give us the elements that form the bases of the matroid, by simply, whenever a minor of the matrix is non-zero, the corresponding set of columns gives us a basis of the matroid. So an example for a realization of a uniform matroid U24 over Q would be this 2 by 4 matrix, because whenever you pick two of the columns, they're linearly independent, so they give you a basis of the vector space Q2. Okay. Now, as a realization space for matroids, this was already introduced in more detail yesterday in Benjamin's talk, is, okay, so for our talk, we're going to fix the closure of the rational numbers, and we denote the realization space of the matroid as R of M. And we've seen yesterday that this comes from the Grassmannian. Okay, so we have the Grassmannian Rm, the space of Plücke coordinates for matrices, for R times M matrices, and we've seen the Plücke relations yesterday in Benjamin's talk. Okay, and then the Grassmannian for the matroid M is this space of Plücke coordinates for matrices that realize M. So all the entries in our vector of Plücke coordinates, those are non-zero whenever the corresponding indices are a basis of the matroid, and they're zero otherwise. Okay, so this is the Grassmannian for the matroid M. Now, two matrices give us the same point configuration. When we think about a matrix that realizes our matroid as a point configuration in projective space, yeah, then two matrices give the same point configuration whenever there's a scaling of the columns, right? The scaling of the columns is just I take a different representative of my point in projective space. So in terms of Plücke coordinates, this means that every minor is multiplied by the corresponding product of scalars lambda, non-zero scalars lambda that live in the torus. Okay, so our realization space is actually the Grassmannian modulo of this torus action. Okay, so this action of scaling the columns. And by Neff's universality theorem, this realization space can have arbitrarily complicated topology. Later in the talk, we'll see that we can compute some of these realization spaces for at least small matroids. Okay, so far, so good. This is more or less known from yesterday's talk. Now comes something more specific that we want to tell you. I promised you self-dual matroids. So I will say for brevity self-dual, whenever I mean identically self-dual, in which this means that the set of bases is closed on taking the complement. So whenever I have a basis and I take the complement, this has also to be a basis. So 1, 2, the complement is 3, 4. This is going to be, of course, true for the uniform matroid 2, 4. And here we also see something particular that's important. The number of elements of the ground set has to be twice the rank of the matroid. Otherwise, this cannot be self-dual matroid, right? Because the complement of the basis has to have the same size as the basis itself. Otherwise, it can't be a basis of the matroid as well, right? Okay. I saw confused faces. Is this clear? So we always need to have n to n. For example, uniform matroid n to n will always be self-dual. The uniform matroid 1, 3 can't be self-dual, right? Because the complement will have size 2. A non-example would be this matroid here with the set B2, because the set 1, 4, the complement is 2, 3, it's not a basis. So it's not a self-dual matroid for this talk. Okay. We're interested in particular in realizations of these self-dual matroids. And one thing that we need to know is that there is something also called self-dual point configurations. And of course, we want to understand how these relate to realizations of self-dual matroids. So self-dual point configurations under different names have already been studied 100 years ago by Coble and by Dolgachev and Ortland, where they were called associated or self-associated point configurations. We call them self-dual because that fits very nicely with the theory of self-dual matroids. So when we have two endpoints in projective space that span Pn-1, they're said to be self-dual whenever they satisfy this matrix equation. So I can find non-zero lambdas, put them in a diagonal matrix, put my points in columns, and take the transpose, and then the product of this will be 0. If you've seen Gale duality before, this is the same. Okay, so let's see an example. We had before our realization of the uniform matroid 2, 4 is this matrix. And now by some magic, I was able to find these non-zero lambdas. And if you do the math of this matrix multiplication, that should give you the 0 matrix. It's not a coincidence that the realization of my matroid that I picked here allows me to find these non-zero lambdas. In fact, it turns out whenever you pick 4 distinct points in P1, you will be able to solve this equation with non-zero lambdas. So in other words, any 4 distinct points in P1 are self-dual. If that were true in higher dimensions as well, it would be pretty boring or pretty interesting, depending on your point of view. But it's not true in general. So for n equal 2, any 4 distinct points in P1 are self-dual. But when we go higher up for n equal 3, so we have 6 points on the plane, they're self-dual whenever they lie on a conic. Okay, so these have to be co-conic. And 8 distinct points in, this should be a P3. Okay, 8 points in P3 are self-dual when they form what's called a Cayley octet. So there is some geometry behind these self-duality conditions. Okay, so the natural question that we now ask ourselves, that we know self-dual matroids and self-dual point configurations, is can we always realize a self-dual matroid that's realizable as a self-dual point configuration? And that's to understand this is we need to understand the parameter space of these self-dual points, or to put it in a relation with the realization spaces of matrices. So we have this matrix equation. Okay, X is our point in our point configuration. Lambda is this special diagonal matrix. Okay, and the transpose. This needs to be 0. So we want to translate this matrix equation in terms of Flickr coordinates to have something in the Grassmannian. Okay. Now what this means, this matrix equation simply means that the vector space to X lambda is the orthogonal complement to the vector space that belongs to X. Okay. And well, taking the orthogonal complement is an involution on the Grassmannian n to n. Okay, that maps X to X orthogonal complement. It's the Hodge star map. We denote it by P maps to P star. And well, it's given like this. Okay, so the index P star I is some the signum of a permutation, and then the Flickr coordinate of the complement. This looks rather complicated. Just look at the example. Okay, so for P12, the first entry will be substituted by P34, which is the complement, and the sign is positive. The next, the sign will be negative, and so on. Okay, so 1, 3, 2, 4, and the negative sign. This is P star. This is the Flickr coordinate for the orthogonal complement. And now we can translate this matrix equation simply into the condition P star has to be lambda P, okay? Because multiplying with this diagonal matrix, we're scaling the columns. That's the torus action on the Grassmannian given by lambda, by this torus element, okay? So a point in the Grassmannian is self-dual whenever there exists non-zero lambdas such that we can write P star as equal to lambda P. And this forms a subvariety of the Grassmannian, the self-dual Grassmannian, which is given by all the self-dual points. And it's a rational variety and has dimension n choose 2 plus 2 n minus 1. Okay. So this is the parameter space of self-dual point configurations. And now we're asking ourselves, right, how to put this in relation with the realization space of the matrix. Okay, right? In general, of course, this will sit inside. It's a subvariety. The self-dual Grassmannian is a subvariety of the Grassmannian. So the space of self-dual realizations of the matroid will sit inside the space of realizations of the matroid. Okay, so let's start with the baby case. That was n equal 2. Right, n equal 2 was corresponded to 4 points in P1. We remember they were all self-dual. Okay, self-dual matroid, rank 2. On 4 elements, there was only the uniform matroid. So it's really just the case. We have only the uniform matroid in this case. The realizations and the self-dual realizations are the same. So for n equal 3, we need to look at all self-dual matroids of rank 3 on 6 elements, and there are 2. There's the uniform matroid, right, with realization dimension 4. And now we remember 6 distinct points on the plane are self-dual whenever they lie on a conic. That's a codimension 1 condition. So the self-dual realization space is of dimension 3, strictly smaller. There is a second self-dual matroid for rank 3 that has 2 non-bases, 1, 2, 3, and 4, 5, 6. And in this case, the dimensions of the realization and the self-dual realization space again coincide. Yeah. Because what does it mean? 1, 2, 3, and 4, 5, 6 are non-bases. It means these points, they lie on lines, right? So we're on a plane. And these are not in general position. That's why we're not in the case for the uniform matroid. But they still live on a conic, right? They live on 2 lines. And this will always be self-dual realization. And all these realizations look like this. So the next case would be n equal 4. Now for n equal 4, there are some more matrices that we need to consider. Namely 13. And this data is stored on the database PolyDB. They have all the rank 4 matroids on 8 elements. And we can ask them simply for all the self-dual ones. And there are 13, and they're listed here. And we computed the dimensions of the realization and the self-dual realization space. So the first line shows you the uniform matroid, which has realization space of dimension 9. And I told you if they're in general position, 8 points in P3 are self-dual whenever they form a Cayley octet. And being a Cayley octet is a codimension 3 condition. So correspondingly, the dimension here is of the self-dual realizations of dimension 6. So there are two other things that I want to point out to you here on this list. The first one is this line here. We see dimensions are set here to -1. That is because this matroid is not realizable over characteristic 0 because it contains the Fano matroid. Okay, so this one is a case that we will remember, hopefully, if I get to the end of the talk at the very last slide. Okay, keep this in mind. The last one here is also a bit special. You probably can't see it from the list of the bases, but this belongs to the direct sum of 2 uniform matroids of rank 2 on 4 elements. And it's this kind of condition where we have 2 quadruples of points that live on a line. It's a very special line condition. Okay. Yes.
And when the dimension, yes, the question is, are the realization spaces integer? When the dimension is the same, are they actually?
In rank 4, yes. We computed Grobner bases, so that, and we see that when the dimensions agree, the Grobner bases give the same variety. Good question. Okay, so that's rank 4. Next step would be rank 5. So the one problem that we're running into with rank 5 is if we go to the database PolyDB and we want to pull all the rank 5 matroids on 10 elements and ask for the self-dual ones, this is not going to work. There are just too many matroids of rank 5 on 10 elements. So what we did instead is we constructed the list of only the self-dual matrix of rank 5 on 10 elements by using the database for rank 5 on 9 elements, okay? Which exists on PolyDB. And from that, we built the self-dual matrix of rank 5 on 10 elements, and there are 1,042 of these. Again, we computed the dimensions of the realization and the self-dual realization spaces. And here you see the dimensions for the realization spaces for the non-uniform matroids. The uniform matroid has dimension 16, didn't fit on the slide, so not on here. And the computation for the self-dual realization spaces got a lot more extensive, and it was not possible for us to actually really compute Grobner bases in all these cases. So we know this for 753 matroids. And for some of them, we got the dimensions heuristically, so by slicing with hyperplanes, with generic hyperplanes. So the knowledge of the dimensions exceeds the knowledge of the actual self-dual realization spaces that we have, because these computations are really expensive. But the one thing that we can see here already, it's very interesting. You see there are 346 matroids that are not realizable. But you see there are 349 matroids that don't have a self-dual realization. That means there are at least 3 matroids that are realizable and self-dual, but cannot be realized as self-dual point configurations. This is something that we did not observe for rank 4 or smaller. We see this the first time for rank 5, and we assume that this will continue and even get, this gap will get bigger for higher ranks. And here the question that was asked before for rank 4, here for 718 of the matroids, the closures of the self-dual realization space and the realization space really coincide. Okay, so if you're interested in this data and you want to, know more about these and investigate them yourself, there are 2 ways of doing this. So we have a math repo page where we have a small database that you can run a Python script, and you will get like the Grobner bases of the realization and the self-dual realization space. And you can get also templates for the matroid, like here. So you can see this still contains a variable x25, which you will have to set according to the Grobner basis. So this template's only solving the linear part. Everything more complicated you'll have to do yourself. But you have all the information here. And second place where we put the data, or with a different focus, is on the database PolyDB. There is now a collection for small self-dual matroids. And there is, for example, you can find all these 1,042 self-dual matroids of rank 5 on 10 elements. And you can ask, for example, I want a matroid with that's self-dually realizable, not self-dually realizable, but realizable. And then it will pull me out this one of those three matroids for which we know that it's realizable self-dual matroid without self-dual realization, right? And you can get like the Todd polynomial and all these nice invariants for matroids. No, only characteristic 0. We only tested for characteristic 0. We needed to limit ourselves. Okay, so that's all I wanted to say for distinct points. Now you can say, okay, we started with these distinct points in projective space, but it might happen that I have a degeneration, right? So for example, again, in the baby case, 4 points on P1, I have my 4 distinct points. And now what can happen is that the situation of my points is that they degenerate and 3 and 4 come very, very close together and finally collide. A matroid, the matroid that I get from this configuration is no longer self-dual. Okay, what does the algebraic geometer do if he sees this picture and thinks, I kind of want these points to remember that they have been distinct? He blows them up, right? There's a blow up, which we've heard about earlier today. But we're not going to go into the theory of this, just the picture, okay? And now we can remember 3 and 4 as distinct. And I get the same picture if I look at the reverse, right? Let 1 and 2 collide, and it's kind of the same picture. Okay. But how can I now consider all this in terms of matroids and combinatorics? For this, we need the concept of the matroid polytope, which we already also saw yesterday. Again, the same baby example picture that we've seen in Benjamin's talk, because it's the only one we can draw. The matroid polytope of the uniform matroid 2,4. Uniform matroid 2,4 belonged to this point configuration. Okay, matroid polytope, a vertex for each basis. Okay. Right, now what happens if my points 3 and 4 collide and I look at this polytope and I remember every vertex supposed to be a basis? Well, what happens is vertex 3, 4 is going to vanish, right? Because it's no longer a basis. So all I remember is this upper pyramid. And if I look at the reverse, right, and 1 and 2 collide, well, the upper vertex is going to vanish and I remember only the lower one. So the corresponding picture to this blow-up version on the combinatorial side is to remember both pyramids as single pyramids that glue together to form the octahedron, right? So this is called a matroid subdivision, right? So I remember this subdivision. I remember that I have 2 parts that form the whole. And this helps us to understand these degenerations. That's the idea slide. Now we go into the definitions. Okay, so we've seen already the matroid polytope, right? For a matroid, 1 to n. The matroid polytope is given by the convex hull of all these sums EB over the standard basis vectors, where I is in the basis of M. And as the example for our uniform matroid 2,4, we get the octahedron, right? So this is, as we see, this is an R. The matroid polytope lives in R2n modulo the all ones vector. So for U24, this is a 3-dimensional polytope that lives in 4-dimensional space modulo this hyperplane. Okay, so a three-dimensional polytope that we can draw. A subdivision of the matroid polytope is a matroid subdivision when each cell itself is again a matroid polytope. So in this picture that we've seen before, you would have to verify that the collection of bases that you get from the upper and respectively lower pyramid again satisfies the basis exchange axiom, which it does. So this is a matroid subdivision of the octahedron. And it's one of three ways to subdivide the octahedron. We saw all three of them, right? You can slice like this, like that. We saw them yesterday also on Benjamin's slides. Now, again, we need to go to parameter spaces. The Dressian, which we again have seen yesterday, is the parameter space of the regular matroid subdivisions of the hypersimplex delta n2n. This is the matroid polytope for the uniform matroid n2n, okay? And the elements, so all these, that give us these regular matroid subdivisions are called valuated matroids. Again, I think the best way in this way to imagine this is just to look at an example. So again, we have our baby case, we have U24, we have the bases, and each of these bases, or respectively the vertices of the matroid polytope, get assigned a height. And according to this height, we get this one dimension higher, look at the lower faces, and we obtain the subdivision, okay? And now this element, this vector up here, the 1, 0, 0, 0, 1, is the valuated matroid, the element of the Dressian 2, 4, okay? All right. Now, the tropical Grassmannian consists of the realizable valuated matroids. Okay, so it's a subset of the Dressian and consists of the realizable valuated matroids. In the baby case 2-4, the Dressian and the tropical Grassmannian coincide. Even for 3-6, this is still true. Okay, the tropical Grassmannian 3-6 and the Dressian 3-6 coincide. But for 4-8, which will be in our setting, right, n2n, this is the step. This is no longer true, and it's already not true for 3-7, but this is not a self-dual case, so we don't consider it. And it will not, and this inclusion is strict in general for higher n as well. Okay. Okay. So far the definitions. Now, if we want to understand self-duality, in the degeneration case, we need to understand how to move the self-duality into the setting of the tropical Grassmannian and the Dressian in order to understand these degeneration cases. So what do we say is this, when is a point self-dual? Okay, before we had this equation P star equals lambda P, right? That was the equation we had before. And now we say a point is self-dual whenever Q minus Q star is in the lineality space of the Dressian. Okay, so the Dressian is a polyhedral fan, and it contains a vector space. Each of the cones contains a vector space, the same vector space, and this is called the lineality space of the Dressian, okay? And this lineality space is the role of the lambda of the torus action from before, right? Before we had P star is the same as P up to a torus action, right? Some non-zero lambdas. And now we say Q is the same as Q star up to something in the lineality space. Okay? So the lineality space of the Dressian takes now the role that before was this torus that we had, okay? And now then we get the following sets: the self-dual points of the tropical Grassmannian and the self-dual points of the Dressian, simply intersecting with this condition. Now, for those of you who know about tropicalization, you can say, wait, but there is another set that I can look at. It's the tropicalization of the self-dual Grassmannian. Not going to get into the detail of tropicalization here, but basically what we get is this chain, right? What happens here, so first we know the tropical Grassmannian lives in the Dressian, so that when I look at the self-dual points, this inclusion here is still going to be the same, right? I have inclusion before, I intersect with the same thing on both sides, inclusion is still going to be there. on this side, what happens is the following. Here, I tropicalize the Grassmannian, and then I intersect with the self-duality condition. Here, I first intersect with this classical self-duality condition, and then I tropicalize. And tropicalization and intersection a priori does not commute. So this is an inclusion, and it might or might not be an equality. We don't know in general. Okay, so this is a question. Okay, so what's this? Apart from this fact that Q minus Q star lives in the linearity space of the Dressian, what is the special thing about self-dual valuated matroids? And there is a very nice geometric property that these valuated matroids have, and it's the following. Whenever you fix your self-dual valuated matroid and you look at the collection of matroids that you gain from the from the associated matrix subdivision on rank n, okay, so I take all the rank n matroids that appear in my matrix subdivision, then this set is closed under taking the dual. So when I find a matroid in the subdivision, I take the dual of this matroid. It will be somewhere in the subdivision. There will be exactly this dual matroid. Okay. If we think back on the subdivision of the octahedron, I had these two maximal cells, the upper pyramid and the lower pyramid. The dual of the upper pyramid of the matroid that belongs there is the matroid that belongs to the lower pyramid, and vice versa, right? So this is exactly what we see here. Okay, okay. And now this, now we can look again at the degenerations of point configurations. And we can, now that we have all the definitions and a bit more understanding, we can take a step up from 4 points on P1 and look at 6 points in P2. So we have 6 points on a conic, right? So they're here. And I picked a parameterization with T so that you see if you let T go to 0, points will collide, right? Point 1 and 2, point 3 and 4, and also the points 5 and 6. So when T goes to 0, here it's easy to see, right? What happens here below, you have the Blöcke coordinates of the corresponding point in the Grassmannian. And if T goes to 0, always the red entries here, they survive, everything else goes to 0, everything else vanishes. So in particular, we see that the bases of the matroids, okay, so 1, 2, 3 is what corresponds to the first entry. It's not a basis of the matroid, obvious, since 1 and 2 collide, right? But things like 1, 3, 5 here, corresponding to this red 2, that will still be a basis of the matroid. Now, since I consider my points to be on projective space, I can choose also a different representative, okay? And before I let T go to 0, T is invertible, so I can choose this representative, right? And now I can say, okay, what happens if I let T go to 0 here? So if T goes to 0 here, in the matrix, you don't see much, but look at the Blöcke vector down here, okay? And what happens again, everything that is red survives, everything else goes to 0. And we see that we will see a different matroid. We will see a different point configuration because 1, 2, 3 is still a basis. And if you go through all the entries, it turns out that 1 and 2 stay distinct in the limit, 3 and 4 collide, and 5 and 6 collide. And so we see a different degeneration of our 6 points on the conic with this representative. We see a different matroid. However, what happens if we take these two Blöcke vectors and we look at the corresponding matroid subdivision that they induce on the matroid polytope of the hypersimplex 3,6. Okay, so how does that work? Well, we look always at the lowest exponent of T that appears. Yeah, and that gives us the height function, right? The height function for our matroid polytope. And it turns out both these vectors will give you the same subdivision because, well, since these 2 point configurations that we started with only they're the same modulo this torus action, these 2 points are the same modulo of the linearity space. Okay. And the two different matroids that we see highlighted in the limit are just different cells of the matroid subdivision. Okay. So the corresponding matroid subdivision, I can't show it to you properly because I cannot draw the hypersimplex 3/6, but we can look at this tight span where each of the black circles stands for a maximal dimensional cell of the matroid polytope, matroid subdivision. An edge between them means they share a facet, and this interior is a codimension 2 cell that's shared by all the 6 maximal dimensional polytopes. Now, each of these polytopes in the polytope subdivision correspond to a different degeneration of the point configuration. So the first one that we saw was the one where we had 3 tuples of points that collided, and it's the one corresponding to this interior cell. And the other one that we saw was highlighted this matroid up there, right? 1 and 2 staying distinct, 4, 5, 3, 4, and 5, 6 colliding. So choosing different representatives and taking the limit just highlights different matroids in the matroid subdivision. And this matroid subdivision remembers all the possible degenerations of your point configuration. Okay, now how does this fit into the tropical Grassmannian 3/6? Okay, so there are 7 types of cones in the tropical Grassmannian 3/6. These are tight span pictures. So this one is the cone that we've seen before, right? The hexagon. And there are 6 others. And the one important thing is, right, that each of these vertices corresponds to a matroid. And we know if this has to have a chance of having a self-dual evaluated matroid belonging to it, we know that the dual of such a matroid needs to be somewhere else in the matroid subdivision. This was the proposition that I've shown you earlier. And it turns out this is only possible for 2 types of these cones, the hexagon and this one up here. For all the others, there are some matroids that if you take the dual, it's not in the list of your collection of the matroids. Okay, so these 2 cones are the ones that when we take the tropical Grassmannian and intersect with the self-duality condition, these are the only maximal dimensional cones that we meet. And here we see them again with the corresponding degenerations of the point configuration. Okay? So these 2 types of maximal cones exist in the tropicalization of the self-dual Grassmannian 3/6. And if you've been attentive, you might have noticed that before I said, okay, we have the tropical Grassmannian, we intersect with self-duality condition, which would be trop GR 3/6 upper SD. And here I'm claiming this is the tropicalization of the self-dual Grassmannian, which is like first intersecting and then tropicalizing. And this is already part of our theorem here, where we computed all these 3 spaces, and it turns out for 3/6 they are the same. Okay, so tropicalizing the self-dual Grassmannian is the same as intersecting the tropical Grassmannian with the tropical self-duality condition is the same as the self-dual points of the Dressian. And this is a balanced span of pure dimension 8, which modulo its linearity space is a fan over a 2-dimensional simplicial complex with these numbers of vertices, edges, and triangles. And it has a very nice parametrization by the tropical Pachter-Speyer map from the tropical Grassmannian 2/6, which is the space of phylogenetic trees with 6 leaves, where each of these trees corresponds to one self-dual configuration in the tropical Grassmannian. And this works like this. So we have 2 types, the 2 types of trees with 6 leaves, the caterpillar tree and the snowflake tree. And there are 90 caterpillar trees, which correspond to the 90 cones with this tight span, and 15 snowflake trees corresponding to the hexagon in the subdivision. Okay, so the tropical self-dual Grassmannian 3/6, pretty well understood. What about the case 4/8? So the tropical Grassmannian 4/8 is something that we cannot compute completely. So this is a hard question. The tropical self-dual Grassmannian is a codimension 3 variety, subvariety of the tropical Grassmannian, so it's smaller, but still we don't know it entirely. But we can take a step back, look at the classical picture, and see if maybe there is a way to understand this tropical variety. Okay, so we recall that 8 points in P3 form a Cayley octet, are self-dual whenever they form a Cayley octet. Okay, and a Cayley octet was introduced by is in the paper of Plowman, Sturmfeld, and Vincent. It's shown that the Cayley octet is already uniquely determined by 7 of its points. So we actually, what this means is whenever you have 7 points in a general linear position, there is a unique 8th point such that this configuration will be self-dual. And well, there's a very nice formula how to compute this, but the main thing is, if you know 7 points, you can compute in general linear position, you can compute the unique 8th point to get a self-dual configuration. So there is a birational map here from the Grassmannian 4-7 into the self-dual Grassmannian 4-8. We call this the Cayley octet map, and well, we compute how the map looks like. There are these probably very hard to read. There are these binomials in the Plücke coordinates for x1 to x7 that appear here in the denominator. And whenever these vanish, it means that the points were not in general enough position. For example, I think if they all vanish at the same time, the 7 points lie on a cuspidal cubic, something like this. I have to check, but something like that was the case. They're just not general enough. Did I do that? Okay, so yeah, that's the when it's not general enough, that's where the map is not defined. Okay. 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 So we have classically, we have this nice map. And now it would be really great if we could tropicalize this, because we do understand the tropical Grassmannian 4-7. Okay. This we know. So it would be great if we could tropicalize this. So let's just be naive and say, okay, we can just, put trop on this formula and see what happens. Okay, what happens is the following. So we take a point in the Dressian 4-7, and we map it to this point. This is the tropicalization of what we've seen before. Yeah, we have Qi minus the sum. Before we had this Pi divided by. So this is just the tropicalization. Okay. There is a problem. In general, this map, it's not well defined. Okay, so if I pick a bad starting point, I will not end up in the Dressian. Okay, so let's look at this matrix, for example. Then the picture or the image under this map does not live in the Dressian 4-8 because, well, we have 3-term Plücke relations that have to be satisfied on the Dressian, right? And if I pick this 3-term Plücke relation here, the minimum is achieved only once and not twice. And we need minimum achieved twice in order to be on all the 3-term Plücke relations in order to live in the Dressian. Okay? So this naive tropicalization does not work. So there is some more work to do in order to use this Cayley octet map tropically. What we conclude so far is that we know, well, the tropicalization of the image of the Cayley octet map is the tropicalization of the self-dual Grassmannian. The balanced fan of dimension 16 has 7-dimensional linearity space, and we have this chain of inclusion. So we have the tropicalization of the self-dual Grassmannian, which lives inside the self-dual points of the tropical Grassmannian, which is lives properly inside the self-dual points of the Dressian. And this last inclusion, that's the final proof, the final part of this talk, which is where I beg you to remember, which I said at the beginning, there was this one matroid of rank 4 on 8 elements that was not realizable over characteristic 0. We need it now. Okay, so we take this matroid, Okay, this not realizable over C matroid of rank 4 and 8 elements, self-dual. And now we can just build our point in the self-dual Dressian that's not in the tropical Grassmannian. Okay, so we construct this point. We set Qi 0 if I is the basis of the matroid, and 1 otherwise. Okay? And this induces a matroid subdivision on the hypersimplex, which contains the matroid polytope to this non-realizable matroid. And well, this is exactly the point why this does not live in the self-dual part of the tropical Grassmannian, right? Because we have this non-realizable matroid polytope in the subdivision. And that's all I wanted to tell you. Thank you for your attention.
Are there any questions? So in this example of the 3-6 that you did